Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss address sequencing in microprogrammed control unit. So, in previous class, we have discussed about the control units. So, implementation of control unit. So, we can implement the control units in two ways. One is the hardware control unit, and another one is a microprogrammed control unit. So, in this session, we are going to see how we can generate the address of the next micro instruction while the current micro instruction is executing. Okay, so already we have seen about this. So the major, suppose if you consider a basic computer system, so that consists of mainly three functional parts, that are CPU, central processing unit, memory, and input and output devices. So these are the three functional parts: CPU, memory, input and output devices. So if you consider the CPU, again the CPU is having three important parts, that are control unit, ALU, and the third one is the registers. So internal registers. So these are the three main important parts of the central processing unit. Okay, so already we have seen that. So here the control unit. So the main purpose of the control unit is to initiate a sequence of micro operations. So mainly it is used to initiate a sequence of micro operations. So already we have seen what is micro operation. So micro operations are the operations that are performed on the data stored in registers. That is called micro operations. So there is a sequence of micro operations to initiate a sequence of micro operations. We are using this control unit, and also the control unit will generate different timing and control signals, because these timing and control signals are required in order to coordinate different modules inside the computer. So we have so many digital modules inside. So that like some decoders, encoders, registers. So we have many modules. So in order to coordinate all that modules, we require some timing and control signals. So that timing and control signals are generated by using this control unit. So this control unit we can implement in two ways. One is the hardware control unit, and another one microprogrammed control unit. So hardware control unit means the control signals are generated by using the hardware components like some registers, encoders, decoders, multiplexer, demultiplexer, finite state machines. So that means here in the hardware control unit, we are generating these control signals using some hardware components. So that's why it is called hardware control unit. So the main advantage of the hardware control unit is high speed of operation. So the speed is very fast. But the problem is we cannot update the control unit, because everything is involved with the hardware. So that's why it is very difficult to update. So there is no possibility. So that is with the hardware control unit. And coming to the microprogrammed control unit. So microprogrammed. So as the name itself, it specifies the meaning. Microprogrammed. So here the control signals are generated by using the microprogram. So using the microprogram, we can generate the control signals. Okay. So and also the main advantage with the microprogrammed control unit is there is a possibility to update the control unit, because here we are using the microprogram. That means simply by changing the program, we can update it. Okay, and also in advanced process, we are using this microprogrammed control unit. Okay, so if you look into the microprogrammed control organization, so this is a microprogrammed microprogrammed control organization. So mainly it consists of next address sequencer, or we can also call the address sequencer, next control address register, control memory, and control data register. So here we are generating the control signals using some micro program. So in order to store the micro program, we require memory. So here that is a control memory. So the memory we are using control memory. So what is control memory? The memory which is present inside the control unit. So that is a control memory. So here the ROM memory can be considered as the control memory. Okay, ROM, read only memory. That means it is a permanent memory. Okay, so see here. So ROM can be considered as to store the micro program. Okay, so if you look into the structure of the memory, so it is having like this micro. It is a memory. So the memory, it contains multiple memory locations. Suppose if you assume, okay, so the size of this ROM is it is a 128 volts. So the size of the ROM is 128 volts. So that is nothing but the memory, it contains total 128 memory locations. So starting with 0, so 0 to 127. So total it contains 128 memory words. Okay. Memory word is nothing but memory locations. Okay. So in this control memory, we are storing a micro routine. So we are storing micro routine or micro program. So using that micro program, we are generating a control signals. Okay. So here, so this for every micro routine to store every micro routine, it requires 4 memory locations. So that means 128 divided by 4. Okay, so that is equal to 32. So that means total in this memory we can store 32 micro routines. So we can store 32 micro routines or 32 micro programs. Okay. So here, so using this micro program, we are generating the control signals. Okay. So that is a micro programmed control unit. So here in this, see here. So the address are 001, 002, 003, 004 up to 127. So total it contains 128 memory locations. So here when the CPU is executing the micro instruction in the first address, so that address will be stored in the control address register. Okay, so the present micro instruction address will be stored in the control address register. Okay, and next control data register. So the memory, the micro instruction. So the micro instruction which is stored in the memory location will be stored in the control data register. So in the control data register, along with the micro instruction, we are having some additional bits. So that additional bits, it may be a 10 or 11, so like that. So that bits will be given to the input of the address sequencer. So this is a next address sequencer. So that means what it will do, the next address sequencer. So while the first micro instruction is executing, simultaneously the address sequencer will generate the address of the next micro instruction. So What is the address of the next micro instruction? That is a 002. So this next address of the next micro instruction, it is generated by the address sequencer. Okay. Okay. Again, whenever it is incremented, then 002. So again, this address. So that means the CPU is executing the micro instruction which is in the address 002. So now this 002 will be stored in the control address register. So that means CAR. Next to that corresponding instruction, it will be stored in the control data register. So in this way, at a time, two operations are going on. Two operations are performing. So executing the current instruction, simultaneously generating the address of the next micro instruction. Okay. So this is a process how we can generate the address of the next micro instruction. So here the control memory is assumed to be read-only memory. So here we are ROM is considered as the control memory because it is a permanent memory. So here we are storing all these micro routines or micro programs. Okay. So where all the control information is stored permanently, ROM provides address of the micro instruction. So this is we are storing. So we are storing a micro program. We are storing a micro program or micro routine in the control memory. So micro program is nothing but it is a collection of micro instructions. Collection of micro instructions. So every micro instruction it will generate one or more micro operations. It will generate a micro operations. Okay. So basically we are storing a program. We are storing a program. We are storing a program in memory. So program is nothing but it is a collection of instructions. Collection of instructions. So the instructions, the CPU it cannot directly execute the instructions. So first the instructions will be converted into the machine language instructions. Machine language instructions. So this machine language instructions require the micro routine or micro program. Okay. So the machine language instructions require the micro instruction, micro program or micro routine. Okay. So this is a relation between a program and the micro operations. Okay. So the address sequencing in microprogrammed control unit. So the control memory it is used to store the micro instructions in groups. So here each group is used to specify a routine. So routine means it is a group of instructions, group of micro instructions. That is called routine. Okay. So the control memory of each computer has instructions which contains their micro programs routine. These micro programs are used to generate micro operations. So just before we have seen a flow of how the program will be converted into the corresponding micro operations. Okay, so that will be used to execute the instructions. Suppose the address sequencing of control memory is controlled by the hardware. In that case, that hardware must be capable to branch from one routine to another routine and also able to apply a sequence of micro instructions within a routine. Okay. See, so when we try to execute a single instruction of the computer, the control must undergo the following sequence of steps. So whenever we are trying to execute a single instruction, then we should follow the following steps. First one is when the power of the computer is turned on. So as soon as we turn on the computer, so first load the initial address. So we have to load the first address into the CAR. CAR means control address register. So whenever we turn on the computer, so we have to load the first address into the first address of the memory into the control address register. Okay. So this address can be described as the first micro instruction address. So already we have seen previously. So we have a memory. In this, this is a control memory. So in the control memory, we are storing a micro instruction. So it is a micro instruction 1, micro instruction 2, 3. So the address of the first micro instruction will be stored in the control address register. Okay. Next. So with the help of this address, we are able to activate the instruction fetch routine. So with this address, let us assume the starting address is 001. Okay, so with that address, it will activate the instruction fetch, because whenever there is an instruction, it has to undergo some 3 steps: fetch, decode, execute. So first step is the fetching. The instruction has to be fetched from the memory first. After that, it has to be decoded, and finally it has to be executed. Second one is the control memory will go through the routine, which will be used to find out the effective address of the operand. So once the instruction is fetched from the memory, after that it is required to find the effective address of the operand. Operand is nothing but the data on which we are performing the operation. So in the last step, the micro operation will be generated. The micro operation will be generated, which will be used to execute the instruction fetched from the memory. So suppose if you consider a example, add al, comma bl. Okay. Al offset of bl. Okay. So here add al comma offset of bl. So that means the contents of so bl. Let us assume bl is equal to some 98. Okay, so 98 is the address of the it is the address of the operand. So that means where the operand will be there. So this is the address. So that means in the 98 location, our required operand is present. Okay, so see here. So here the contents of this memory location will be added with accumulator AL. So what is the operation add? So in order to perform this addition operation, it requires some micro operation. Okay, so that micro operations will be generated in the last step. And coming to the control memory required the capabilities of address sequencing, which is described as follows. So in the already we have seen in the microprogrammed control unit, while the current instruction is executing, simultaneously the address of the next micro instruction is generating. Okay, so this we can done in 4 ways. The first way is the incrementing the CAR by 1. So the address sequencing is able to increment the CAR. CAR means control address register. So CAR incrementing. So incrementing the CAR by 1. So that is a first way of generating the address of the next micro instruction. And the second one is it provides the facility for subroutine calls and returns. So basically the subroutine is a function. Subroutine is a function, and it can be used for some repeated tasks. And the third one is the conditional branch or unconditional branch. So using this conditional branch or unconditional branch also, we can generate the address of the next micro instruction. And the last one is a mapping process. So mapping process. So mapping process is provided by the address sequence from the instruction bits to the control memory address. So that means suppose if you consider a instruction register. So in the instruction register, the size of the instruction register is 0 to 15. So that means total 16-bit register. So in that 12, 13, 14. So these 3 bits represents the opcode. So these 3 bits represents the opcode. So 3 bits. So using this 3 bits, we are going to form a control memory address. Okay, that process is called mapping process. So the process of converting these opcodes into the control memory address, that is called mapping process. So in the further slides we can discuss about this mapping process with the example also. Okay, so this is a address sequencing. So how we can generate the address of the next micro instruction. So we can see here. So total we have seen 4 ways to generate the address of the next micro instruction. So first one incrementing CAR by 1. Incrementing CAR by 1. So what is CAR? CAR control address register. So this is a control address register. Okay. So control address register. So in order to understand in detail, so let us consider a memory. So already we have seen. So what is the size of the control memory? So the size of the control memory is the 128 volts. 128 volts. So that means total it contains 128 memory locations. So starting with 001, 002, some 098. Last one is 127. Okay, so this is 0, this is 1, this is 002. Okay. Okay, so this is a memory. So this is a ROM. So ROM memory is considered as the control memory, and the size is the 128 volts. So that means 128 memory locations. Okay. So suppose when the first micro instruction. So this is a micro instruction 1. When the first micro instruction is executing, okay, so the corresponding address. So that means what is the address of the first micro instruction? 001. 001. So that 001 will be stored in the control address register. Okay. So in order to get the address of the next micro instruction, what we have to do using the first method, that is incrementing the CAR by 1. So that means this we can increment by using this incrementer. So we are using one incrementer. Okay. So it will increment the current value by 1. So what is the current value? 000. So if you increment that by 1, then a new value will become 001. That is a new that is the address of the next micro instruction. So that will be loaded into the CAR using some multiplexer. So already we know the multiplexer. So this is a 4 by 1 multiplexer. 4 by 1 multiplexer means 4 inputs and 1 output. and two selection lines. Okay. So after incrementing the CAR value, again that incremented value will be loaded into the CAR register. So this is a first way. Incrementing the CAR value by 1. Next, second one, using subroutine calls and returns. Using subroutine calls and returns. Okay, so that is the second one, using subroutine calls and returns. So what is a subroutine? Subroutine is a function in C language, Java, like in any programming language. So subroutine is a function. So whenever we are calling that function, so the control will be transferred from main program to the function, and whatever the statements in that function will be gets executed, and after that it will be returned back to the main program, address of the main program. So let us assume, suppose see here, let us assume in 98 location we have we have called a function. So we have called a function. So what will happen whenever we call a function, the program control will be transferred to the function definition. So it is a function definition. Then in the function definition we have some instructions. So all that instructions will be gets executed, and whenever all the statements in the function gets executed, then it is coming the program control will return back to the address of the next address of the main program. So that means it is in the 98. So next, what is the address of the next micro instruction? That is 99. So it is returned back to the 99 location. Okay. So this is the address of the next micro instruction. So this 099, it will be stored in the subroutine register. It will 099. So it will be stored in the subroutine register. So from the subroutine register to the multiplexer, it will be loaded into the CAR. It will be loaded into the CAR, control address register. So that is a second one. That is the second. Next, third one. Third one is the conditional or unconditional transfer. Unconditional transfer. Conditional or unconditional unconditional branching. We can call branching. Unconditional or conditional branching. So branching means transferring the program control from one memory location to the new another memory location. That is called branching. So here conditional or unconditional. So if you consider a unconditional, so as the name itself, it specifies the meaning unconditional. That means without checking any condition. Without checking any condition, the program control will be transferred to the new address. Okay, see here. So this is from the control memory. So let us assume we have some address. So 126. So this is a 126 address. So that means we have specified to branch to the address 126. So it is a unconditional. That means here we are not checking any condition. Without checking condition, directly the program control will be transferred to the 126 location, because previously where the program control it will be in the 099, but now the program control we are transferring to a new address, that is 126. So this 126 will be given to the multiplexer. Through the multiplexer it will be loaded into the control address register. So based on the this selection lines. Okay, so that is a unconditional. And coming to the conditional transfer, conditional branching. So conditional, so that means here we are checking some condition. If the condition met, then only the branching will takes place. Okay, so see here. So this is a unconditional. This is a conditional branching. So this is a conditional branching. Okay, so this conditional branching. So here we are using some branch logic. We are using a branch logic. Okay, so here some status bits are there. So we have some different status bits are there, that are zero flag, sign bits, 0 bits, sign bits, parity, carry flag, overflow flag. So like that we have different status bits. So using that status bits, it will check the condition. If the condition is true, then only the branching will be takes place. Otherwise, there is no branching. Okay. Suppose if you have a address 000 is there. So what is the 00? It is a result. Okay. If the condition, that means 0. What is 0 flag? If the result is 0, then 0 flag will be set to 1. Otherwise 0. Okay. So it will check this address. So if the result is 0, then the condition is met, then only a control will be transferred to the multiplexer. That means this address will be loaded into here. So that is a conditional branching. So we have seen conditional and unconditional branching. And the last one, fourth, so that is a mapping process. So what is mapping process? So mapping process is using the opcode bits. We are going to find in the address, control memory address. So we can see here mapping process. So mapping of instructions. So in the control memory, if the micro instruction specifies a branch to the first word, in this case, there will be a special type of branch. Here an instruction contains their microprogram routine. So the control memory, it stores the micro programs or micro routines. Okay. So we are going to find the address of this micro routines or micro programs address. So for this special branch, the status bits will be the bits in the operation code, which is the part of the instruction. So if you consider a instruction register. So initially the instructions are fetched from the memory. Whenever the instruction is fetched from the memory, that instruction will be placed in the instruction register. Okay. So the size of instruction register is 0 to 15. So 0 to 11 bits, it represents the address of the operand, and 12, 13, 14 and 15. Okay. See here, 0 to 11 are it represents the address of the operand, and 12, 13, 14, 15. Okay, 12, 13. 12, 13, 14. So these 3 bits represents the opcode, and 15th bit is there. So that is the I bit. So I bit, it represents the whether the instruction is having a direct address or indirect address. So here we are using only these 3 bits. The 3 bits represents the opcode. 12, 13, 14 bits. Okay. So 12, 13, 14 and 15. 15th bit also we are considering as the opcode. So using these 4 bits, okay, so by adding some additional bits, so by adding some mapping bits, then we are going to construct the micro instruction address in the control memory. So that is a mapping process. Suppose if the opcode is 1011, 1011, so that is a opcode. Okay, so for this opcode, we need to find the address of the corresponding micro routine address. Micro routine. Okay, because suppose if this operation is add, suppose 101011. Suppose if this operation is corresponding to addition, then in order to perform this addition operation, the corresponding routine program has to be generated. Okay, so that's why 1011. So here along for this opcode, we are adding some mapping bits. So the mapping bits are zeros. So 10 to the, we are adding 10 to the left side and 2 zeros to the right side, so that it will form the address of the micro instruction. So this is the address. This is the address of the micro instruction in the control memory. Because already know, so total 7 bits are there. Because if you consider a control memory, the address of the control memory also 7 bits. So the address will be 7 bits, address of the control memory. Because already we have seen 128. What is the size of the control memory? So the size of the control memory is 128 words. So 128 means we can write 2 power 7. 2 power 7. So that means the address bits are 7 for the control memory. So here we have only the 4 bits using the opcode. So we are adding 10 to the left and 2 zeros to the right, so that it will so that the number of bits increases to the 7. So that means that corresponding. Okay, so what is the operation 1011? We have assumed add. So for the add operation, the corresponding add micro routine program, which is available in the location 01011100. So here the add micro routine program is available. Okay, so this is a mapping of instructions. So mapping from instruction code to the micro instruction address. Okay, so in this lecture we have seen how the address of the next micro instruction is generated. So basically, so total we have discussed 4 ways to implement the or to generate the address of the next micro instruction. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.